California, as you know, has a much larger population and economy than the whole of Australia. So that's been his focus, but he has also had a global focus, and we've been glad to be a part of that. Would you join me in formally welcoming Jonathan Woolley?
Thanks so much, John. Good morning, everyone. Thanks for hosting me on the beautiful winter's day in Adelaide so we can talk about efficient air conditioning solutions. Thanks for the introduction. My name is Jonathan Woolley. I work with the Western Cooling Efficiency Center at the University of California, Davis. This is a research group that's actually a part of a much larger network of researchers at Davis that are focused on energy and energy efficiency. We've been running now since about 2007. We were started up by a seed grant program out of a group called the California Clean Energy Fund that was set up to start up the very first university-based energy efficiency research program. And we've benefited a lot from that, and over the last several years we've done a lot of really exciting research. So today I'll talk about some emerging low-energy cooling technologies. Though you should know that our mission is a bit broader than just cooling in the western U.S. climates or the California climate, though that's been the key focus for us. We're really about accelerating energy efficiency technology for any thermal system, especially in buildings, but also some other energy distribution type systems like gas pipelines. We're doing a lot of really exciting research. I can't tell you about all of it today. Mostly I'll talk about our indirect evaporative cooling research, our hybrid air conditioning research. But we do a lot of other things, including developing some new technologies, one of which is an almost magical way to seal building envelopes by using an aerosolized glue that fogs the inside of a building and finds all of the leaks and cracks and seals it in an automated way to sort of an unprecedentedly tight standard. We also do a lot of our other work with heating, both with conventional heat pump systems and a variety of other things. So one of the most interesting or kind of effective parts of our organization is that we work very closely with industry. We've worked with Seeley for a number of years now, and we have a variety of different partners, including some major end users, other universities. You can see that we do some collaboration, in fact, with the University of Technology, Sydney, and would welcome doing any collaboration with other researchers. We have representation from a lot of different manufacturers, and we work very closely with utilities all over the United States, and especially in California. The utilities have really been some of the major drivers behind our research. They have a lot of intentions and policy directives to move towards lower energy standards, and they've had a lot of challenges with thermal systems in buildings and air conditioning in particular. So they've been great supporters of our research. So here's the real motivation. Cooling and ventilation in California commercial buildings takes up about 25% of our annual energy consumption. It's a major fraction, and I've highlighted those two pieces in this pie on the slide, not to say that the other pieces aren't important, but to show you what a large fraction cooling and ventilation take up, and to point out the fact that a lot of those other end uses are actually starting to decrease. I mean, look, for example, at lighting. The gains in efficiency we've made in lighting over the last couple decades are incredible, and yet we have not seen broad application of the same type of energy efficiency advances for HVAC. So it's becoming even more important. It's also not just about the entire pie over the course of the year. It's a dynamic problem. At least in California, cooling and ventilation can account for more than 50% of the peak demand from a building on the worst case in the afternoon in the middle of the summer. And that means very much because of air conditioning, we have to generate about 40% more electricity in the afternoons in the summertime than we do during other periods in the year. And that all represents, a major public investment in power plants, an increase in cost for power plants that have to run for a very short period of time. I won't talk too much about it, but the problem becomes, the problem of dynamics becomes even more complicated as we start to introduce more and more renewables, such as wind and solar, onto the grid, which start to reshape the peak and make the contribution from cooling and HVAC even more important. So we also recognize that climates differ throughout the world, and we focus on California, of course, but climates differ throughout the United States, and that there are different technologies that may apply as the most efficient solution differently in different climates. And this sort of runs in the face of the history of HVAC industry, which has really focused on generally a one-size-fits-all solution, vapor compression cooling, to do all of our cooling and ventilation in every climate, no matter what. So we're doing a lot of research with new opportunities there. Going forward. There we go. We also have focused a lot of our research, though it's not seemingly so sexy or interesting as the design of very elegant new building systems. We focus a lot of our research on advances for rooftop packaged air conditioners. And that's to recognize that 80% of the individual pieces of equipment that do heating and cooling in the United States, at least, are rooftop packaged air conditioners. Something like 65% of the total commercial floor area are cooled and heated by rooftop packaged air conditioners. And so if we're going to make a difference in all of the existing buildings in order to drive down our energy use and carbon emissions, we really need technologies that can address this market. So several years ago, we started a program we call the Western Cooling Challenge. We're working with our manufacturer partners, invited and challenged them in solutions that would meet this form factor and reduce peak demand from cooling by at least 40%. And we've been working with a number of different technologies that have kind of come into the fold to be evaluated by our program in the last several years. The first entry was this unit developed by an American company called Colorado, which actually Seeley has very recently acquired. It's exciting to have that new partnership developing. This system we laboratory tested with the National Renewable Energy Lab, and then subsequently ran a number of field tests, showed about 65% energy reduction at peak. Since that very first entry, we've conducted a number of other laboratory tests of different technologies and more than 30 monitored field installations of what we call climate-appropriate technologies just in California alone. And we've learned a lot. The major takeaway, I won't run through all of this, but in every study we're showing some major energy savings using this type of technology. These are along the same numbers that were being presented earlier as you guys were looking at the demonstration, but we ran a side-by-side evaluation of the Climate Wizard and the Colorado system, showed a cooling COP of 15 at peak. And what they didn't mention is another advantage of that system is that you might reach a COP greater than 25 when you're running at part load. So peak, of course, is incredibly important, but there's huge opportunity during part load when that system can run at variable speed. There's a number of other technologies as well. Some of our demonstrations have showed kilowatt-hour energy reductions from day-to-day in data centers between 40 and 70%. There's also opportunities to sort of apply relatively simple retrofits to existing rooftop units by adding an evaporative pre-cooler ahead of the condenser air. And if you do that right, you can reduce demand by between 27 and 38%. Our charge is more than technical as well. And I think this is the other thing that makes our research unique. We actually have a social anthropologist on staff that helps us to understand and evaluate some of the market barriers that stand in the way of helping these technologies get adopted more broadly. This is really important for the utilities who might recognize that there's good technology solutions here, but need to better understand the levers in terms of the different motivations of all the market actors that can be worked to help bring these technologies broader into the marketplace. So I want to run through a few different results for you. If it will go. There we go. This is most recently just wrapped up a laboratory test report where we took the Climate Wizard and added it on to an existing antiquated rooftop packaged air conditioner. We also added on an evaporative condenser air pre-cooler to the same air conditioner, which is a system being developed, not yet commercialized by Seeley, but which they call the CondensoCool. In the laboratory, it showed very similar COP numbers for the Climate Wizard. And when the system is operating together with that vapor compression system over the course of the entire year, we estimate that you're going to reduce your building energy, cooling energy consumption by 65% annually. That's using kind of a load-weighted assessment of all of the different cooling hours in the course of the year for a California commercial building. Here's an example of the results for the wet bulb effectiveness, which is kind of a measure of how close that system cools to the wet bulb temperature. Remember, usually an evaporative cooler would only be able to cool towards the wet bulb temperature, but this shows very clearly that the Climate Wizard cools well beyond the wet bulb temperature. We're getting up well above 110, 120% wet bulb effectiveness. It's really interesting to see the technology capable of doing this by evaporation. We've also done a number of field evaluations, as I mentioned. One, for example, was at Walmart in Southern California. This was a side-by-side evaluation of the Climate Wizard and the Colorado technology. Both of those systems are very similar. They're both variable speed. They both deliver 100% outside air. In this case, they were designed to be integrated with existing rooftop packaged air conditioners, sort of in the same way as the picture I showed before. This is what the packaging looked like. We set these up on the rooftop so that all of the indirect evaporative coolers were sized to provide enough ventilation for the entire store, and they were set up in a way that delivered the product air, or the supply air from indirect evaporative cooling through the rooftop air conditioner and down into the store, which gave us some major advantages in that we used the existing ductwork. It was a very simple installation, if you will, because we didn't have to do any roof curb adaptations, no new penetrations into the rooftop, no new ductwork runs and things like that. And those two systems showed very similar COPs, coefficient of performance for cooling. The black dots here show all of the instances for operating in indirect evaporative cooling at full speed, and the light green, they show all the instances of COP for that observation period when it was running at part speed. In this case, we had controlled the system to sort of two different speeds. And so here you can see at peak conditions of 100 degrees, you would be hitting a COP of about 15. And at part load here, when you're between 75 and 85 degrees Fahrenheit, sort of middle range conditions, you can reach incredibly high coefficient of performance when running at part speed. And in these instances here, part speed cooling operation was adequate to hold the conditions in the space without any additional compressor operation. It's really, really exciting to see. There we go. Another example, and I think this should probably be the last example I give, is a recent installation that we did with Verizon Wireless, which is, you guys don't have Verizon here, do you? So that's a cell phone company in the United States. To add indirect evaporative cooling to cool their cell sites, which are like very small data centers that live in the small fiber bond boxes at the base of their cell towers. Currently the way that they do it is with 2 wall-mounted air conditioners that are designed as a kind of N+1 repetition to make sure that if one fails, they always have a backup. But it turns out, actually, the way they run it is as a first stage and second stage. They're running oftentimes both of those compressor systems at the same time to try to keep that space cool. So they use a lot of energy just trying to keep their electronics cool. We set up an experiment where we added the indirect evaporative cooler as a third system into that space, and we controlled everything in a way that gave priority to the indirect evaporative cooler so that it had the chance to operate first, and then if in any instances it wasn't capable of holding the temperature, the compressors could still come on. And then we set up the entire experiment in a way where in one day we would operate as the baseline with compressor-based systems only, and then the second day we would turn on the indirect evaporative cooler, and then the following day back to compressor systems only, and the following day back to indirect evaporative cooler. And so this chart shows the daily energy consumption recorded. Each bar represents the daily energy, the total energy consumed in each day. The red bars represent the amount of energy consumed by the compressor-based systems, and the green bars show the amount of energy consumed by the indirect evaporative cooler. So this is over the course of several weeks. The blue dots show the average daily temperature, and the extremes, the high and low for those dailies. And so you can see a very clear trend emerging here. Obviously, the days with indirect evaporative cooling use quite a bit less energy than the days without. In fact, it's between 40 and 70% less energy, which is really quite exciting to see. I think I should stop there, given time. How are we?
We've got a few more minutes, I think, and then we'll have Q&A if you have any questions or answers.
I'll give one more example then. Thanks. So we've also been doing a lot of work with other technologies in indirect evaporative or hybrid air conditioning systems that use evaporative together with vapor compression cooling outside of the Seeley and Colorado systems. One example here is technology called the Munters EPX 5000. I imagine many people here are familiar with Munters. We ran a laboratory test of their equipment and then subsequently ran through a field evaluation in collaboration with a Whole Foods market in California. One of the exciting parts about the system is that it is I call it a hybrid because it uses indirect evaporative together with vapor compression, but it's a whole packaged unitary system that's designed as a dedicated outside air supply. So it incorporates the vapor compression together with indirect evaporative cooling in the same unit, whereas all those other examples that I showed were as retrofit additions to existing rooftop packaged air conditioners, and some of the other installations we've done use indirect evaporative cooling in sort of parallel in the same building as an existing packaged air conditioner. Well, here they put it together all in one box. This is a cross-section of how that system works. Again, it's set up as a dedicated outside air supply, so it uses no recirculation. It brings in outside air through a permanent magnet motor fan, which is very efficient, through indirect evaporative heat exchanger core. It's cooled down. If it's not cooled far enough, then they have 2 stages of vapor compression cooling that can operate to drive the supply air temperature to an appropriate point, and then that's then supplied and distributed through the building. This indirect evaporative core does not work in the same way as Seeley's system. It doesn't recirculate a portion of the cooled air back into the wetted channels, which is, by the way, what allows Seeley's system to drive the supply air temperature down below the wet bulb temperature. In this case, it's basically a tube and flow heat exchanger, and they utilize return air from the space as the source to drive the evaporative cooling process. So it can be configured to instead use outside air to drive that indirect evaporative cooling process, but they gain about 30% additional efficiency by instead using return air from the space. So the installation that we did with Whole Foods was pretty cool to see. It's designed to supply the amount of ventilation air that was required for the space, but this system alone was able to keep the compressors from most of the other rooftop units from operating for most of the time. So there's some outstanding advantages to be had here. This is an example of that system plotted, the performance of that system plotted on a psychrometric chart. So you can see at what we consider our peak conditions of about 105 degrees. It's just above 40 C. With the indirect evaporative mode only, they were able to drop the supply air temperature down to 82 degrees. And if you needed cooler air than that, which you would at that condition, you can cycle on the first stage of compressor or the second stage of compressor. And you can see down at cooler temperatures, say 90 degrees, indirect evaporative cooling alone could probably get you to a point that is delivering room neutral air. And at a grocery store, as the example was with Whole Foods, that might be adequate to hold your set points during the middle of the day when it's only 90 degrees outside. We ran all of those numbers through sort of an assessment of how that should impact the energy and demand for a building, considering all the other air conditioners running at the same time. And I'm particularly excited about this system because it represents an opportunity to use a single machine, the addition of one box onto a large big box building. That gives you the opportunity to reduce your whole building on peak HVAC demand by 20% with the addition of one box and hardly any addition, retrofit or controls changes to all the other existing rooftop packaged air conditioners. There's one more technology that I'll point out, which has formed another core of our research. There's another type of hybrid rooftop packaged air conditioner that uses indirect evaporative cooling together with vapor compression, but in a different way. It was tested through the Western Cooling Challenge as a collaboration between Trane and a California company called Integrated Comfort. And here's how the system works. It's a different approach to indirect evaporative cooling. It's designed very specifically as a retrofit to an existing rooftop air conditioner, and it can't really operate as an indirect evaporative cooler on its own, the way that Climate Wizard or Colorado system might. So in orange, we've marked the vapor compression circuit with your compressor, your condenser, expansion valve, and your evaporator coil. You bring your return air and outside air. Usually that would run through your evaporator coil, be cooled down to your supply air. But here we've added on to the outside this blue circuit. Here in front of the condenser, they add a condenser air pre-cooler. It's an evaporative media about 10 inches deep that covers the entire face and circulates water, which evaporates and cools the air coming into the condenser. This improves the efficiency of the vapor compression circuit considerably. But then at the same time, that water is cooled down to very near the wet bulb temperature. And they use that wet bulb temperature water circulated back through to the other side of the system in a water-to-air heat exchanger to pre-cool all of the ventilation air that's entering the system, which reduces the load for the vapor compression circuit. So they call it the dual cool. They're doing two things with it, improving the efficiency of the circuit and reducing the total load of vapor compression. This is some shots from our laboratory test. And the results are again outstanding. At peak, the addition of the system to conventional vapor compression can reduce energy demand by more than 40%. Very similar, maybe more along the lines of 35% reduction at part load. So it's really exciting to see this technology. This one is my favorite in the category of simplicity and cost effectiveness. Among all of the manufacturers that we've worked with, they have kind of delivered the the lowest entry price point. If you have a suite of rooftop units, you can drop this in place as a retrofit relatively easily and at a lower cost. You won't achieve as large a savings as some of these other examples, but they've done a very good job with the simplicity of the system. Do I have a couple more minutes?
Sure.
Fine, thanks. So we've also been considering that it would be really nice if we could operate conventional vapor compression systems in a more climate appropriate way, even without using some type of evaporative system. Of course, I've given a number of examples why evaporative systems make sense in terms of energy savings, but a lot of manufacturers might like another route towards more climate-appropriate efficiency opportunities. Now, a lot of vapor compression systems have been moving towards variable speed, especially including variable speed fans and compressors. Those approaches do improve the cooling efficiency, especially at part load, and they achieve the most significant amount of savings by reducing fan speed during ventilation operation. So all of the periods of the year that you're operating in ventilation only and you don't need to provide cooling, they can reduce energy use by well more than 50%. However, we're showing that if you operate those compressors and fans together in just the right way, you can do some other tweaks and optimization. Especially, you can tune the sensible heat ratio of the system. Now, in hot, dry climates, we would argue that it's very rare you actually need to be doing dehumidification. Quite often, you can get away with not doing any dehumidification, reach your comfort points just fine. But because the way vapor compression systems usually operate, there's a considerable amount of moisture that's removed from the air. When we do all of our assessments, we discount all of that energy that goes towards dehumidification. We look at the sensible only capacity of the system. And we're finding that there's ways to tune the compressor speed and the fan speeds such that you can optimize that sensible heat ratio and do as little dehumidification as possible. These are some examples of laboratory tests that show different fan speeds, different compressor speeds, and the sensible heat ratio that we're able to gain. So while a normal variable speed system might be set up to operate here, and when the compressor speed's running at about 100%, they run a sensible heat ratio of around 70. If we tune things appropriately with the fan speeds, we can actually increase the sensible heat ratio and improve the sensible coefficient of performance for the machine considerably. And what's really exciting is then if you couple this together with a simple retrofit like an evaporative condenser air pre-cooler, you can reduce the total demand for the system by almost 40%, which is really exciting. If you take a condenser air pre-cooler and you add it on to a single speed, constant volume rooftop air conditioner, you might reduce demand by almost 30%. But if you do that with a variable speed air conditioner and tune everything appropriately, it really boosts your performance without reducing your capacity. This is that example. So a baseline rooftop unit plus a pre-cooler plus fan and compressor optimization increases our coefficient of performance by 51%, which is outstanding. So we'll leave it at that. If you guys want more information, feel free to contact me or visit our website at UC Davis. In the last year, we've put together more than a dozen technical reports from all these examples, and they're all available online. I'd welcome your contacting us.
Thank you, Jonathan. Don't go away. Yeah, please, thank you. I promised to finish up before 9, so those of you who need to get away can do that. But that still gives us a few minutes for any questions or comments some of you may have.
Okay, yeah, two different questions. One, how do we move this towards towards policy action. I feel like we're doing it right now. I mean, our core mission is to do the research and to share the research, and to do it all very close collaboration with industry partners. We work very closely with all of the utilities that I'd mentioned there, and there's not a shred of our research that just kind of gets buried in academia. It's all done in direct cooperation with customers and manufacturers and utility partners, and with folks like the California Energy Commission or the Department of Energy. But getting there is a challenge. So the other aspect is the natural cooling methods. Yes, absolutely. I didn't mention much of anything about economizer cooling. It's already a standard and requirement in most building applications, and definitely in California. There's many hours where you can get by with economizer cooling only, but generally it's done awfully. There's a huge opportunity to do better with economizer cooling, which requires absolutely no technology innovation in terms of moving away from the types of systems we have, but it does require better controls, better consistency, better planning and building management. Also, we've done a lot of residential work, and in a lot of hot, dry climates where it cools off at night, there's a huge opportunity in residential to pre-cool and reduce a large fraction of the compressor hours in the following day. So we've done a lot of demonstrations with that type of technology.
Jonathan,
yeah.
I know you sort of skipped over it, but I imagine Adelaide would actually be a sort of a microcosm of California in a way in terms of climate and usage. And you've seen here that our solar take-up has really moved the peak. Do you see that happening in California? And what consequences would it have in terms of how you see this cooling and heating changing?
Yeah, that's a good question. Solar's definitely changing the shape of of what we call the net load profile for generation, right? And California has done a lot of projection into how we expect it to change over the next several years. In fact, we've focused right now on kind of the concept for what they expect around 2020, when we'll have, well, I guess it'll be well more than 20% penetration of renewables. The biggest concern that folks have right now is that because solar is available right in the middle of the day, at the end of the day when the solar availability starts to wane, tends to correspond with especially lighting loads and people coming home from work and things like that. So the rate at which we're going to have to activate our conventional power plants is going to be unprecedented. Though the total amount of energy we'll have to produce during the peak of those days is lower than it would have otherwise been, the rate at which we'll have to switch from not producing to producing may be very tough to maintain power quality and things like that on the grid. So we've been doing a little bit of research into how we can use HVAC to battle that. The interesting part is those most worrisome days in terms of the ramping rate are in the spring and the fall, the swing seasons where HVAC isn't really being used much at all. So there's not much opportunity to shift around HVAC energy use to combat that problem. During the summer periods when cooling loads are massive, the net load profile is anticipated to shift. Namely, solar is going to cut out the middle of the day's peak, and the peak in that day will shift to later in the day, but there will still be a peak. It will still be very much the same. And because the total amount of energy use is projected to grow in California, the total conventional generation requirement is not expected to change, which drives us towards the need for addressing HVAC, because basically all those dynamics mean that it doesn't change our problem with the need for peak generation capacity.
That's policy, right, in California, no new power generation, no new conventional power generation ever. Is that
There's no policy against new conventional power generation, and there is some going in, but there are significant renewable portfolio standards that are driving us towards a 20% annual penetration of renewables by 2020 at least, and there's some move to advocate for even 50% by 2030.
Yeah.